This video is a continuation of the control flow notebook, and we'll discuss the break, continue, and else statements. The break, continue, and else statements allow us to modify the flow and operation of while and for loops. If we look at the diagram here, given a for loop or a while loop, if a break statement is evaluated while executing the loop body, the loop will exit and the interpreter will continue with any code that follows the loop. This gives us a way to exit any loop immediately without reevaluating the conditional expression or exhausting the sequence. If the continue statement is evaluated at any point from within the loop body, then the loop body will stop executing at that statement and return back to evaluate the conditional expression of a while loop or attempt to get the next element from a sequence in a for loop. This is similar to the break statement in that it gives us a way to exit the current iteration of a loop, but this keyword returns us to the beginning of the loop to reevaluate the conditional expression or get the next element in the sequence. The else keyword here is different, and it acts similar to the way it does with an if statement. For a while loop, when the conditional expression is evaluated as false, the else block will be evaluated. With for loops, the else block is only evaluated when the sequence has been exhausted. Okay, now that we've quickly defined each of these keywords, let's take a closer look at each one with a few examples. So as I said, the break statement allows us to exit a loop at any point. If loops are nested, meaning that we have a loop within another loop, then the break statement only exits the closest enclosing loop. As an example, let's create a for loop that will iterate over the integers I equals 0, 1, and 2, and then print them out. And now, during each iteration of this loop, let us iterate over the same range again, but we're going to use the variable j in our nested loop here and print out each of those values as well. Now let's say we're only interested in printing out the values of j from the inner loop if they are strictly less than I, meaning that if j is greater or equal to I, then we don't want to print them out. In fact, since we know the values of j in the inner loop are increasing, we can actually stop the inner loop as soon as we find a j that is greater or equal to I. So I can insert an if statement here just before the print that checks if j is greater than or equal to I. And if it finds that case, we can use the break keyword to break from the inner loop, stopping it from iterating any further. And so now if we run this block, we see that for the first iteration, no value of j was strictly less than I, and so no values were printed out. During the second iteration, where I is equal to 1, the only value of j that was strictly less than I was 0. And in the final iteration, where I equals 2, we see that there were 2 instances where j was strictly less than I. So to see the difference, we're actually going to replace the break statement with a pass statement and rerun the block. And here you'll see that now all the values of j are actually output. Now we're going to discuss the pass statement at the end of this notebook, but the pass statement is effectively a no-op, meaning that no operation is performed. So by replacing the break statement with a pass, we no longer exit the inner for loop when the condition j greater than or equal to I is true. The continue statement, when evaluated in a loop body, will skip to the next iteration of the loop. So to see an example of this, let's say we wanted to iterate over a sequence of integers and print whether those integers are even or odd. We're going to once again start with a for loop, and we're going to use the range function again to say maybe the integer is 2 to 10. And to test whether or not each of these integers is even or odd, we can actually use the mod operator. So we can say num mod 2 is equal to 0, meaning that if the remainder of division by 2 is 0, then we know the number is even. Otherwise, we know it's odd. So if this condition is true, meaning the value is even, we'll simply print even and the number. And now we could use an else statement here and print out odd, but to demonstrate the continue statement, we're actually going to omit the else here and instead write continue. And then outside of the if block, we're going to print odd followed by the value. Now when we run the block, we see that every even value is correctly labeled as even, and the odd values are correctly labeled as odd. So how did this work? When an odd value is encountered, meaning when the mod operation returned 1, the if block was not evaluated, and the second print statement output that the value was odd, after which we loop back around and the next element in the sequence was retrieved. When an even value is encountered, the if condition evaluates to true, and its body evaluated. The first print statement here outputs even, and then the continue statement was evaluated, which effectively skips the rest of the loop body, moving on to the next element in the sequence. So in those cases, it would not execute or evaluate the print function that prints odd. If we repeat this, but we omit the continue statement, you see that the odd values are still handled correctly, but the even values print both the even and odd statements in the output. And again, this example would be better handled by an if-else statement, but this is just a simple example to demonstrate how continue could be used. Now, like if statements, loops can actually have else statements, and their function is actually not too different from their use with if statements. The else statement on a while loop will only be evaluated when the condition becomes false, and it will only be evaluated on a for loop when the sequence is exhausted. So note that in both loops, the else statement is not evaluated if the loop exits due to a break statement. As an example, let's attempt to write a naive brute force search for prime numbers. And since this is a really expensive way to do this, we're going to check a very small number of values, say from 2 to 10. So to start, I'll write for n in range from 2 to 10. And once again, since we're checking a very small number of values, we're going to naively check every value from 2 to n, which is the current element from the outer for loop. And to check each of these values, we're going to see if x evenly divides n. If it does, we'll print out that n is equal to x times n divided by x. And I'm going to use floor division here simply to ensure that the output is an integer, not a floating point value. And then following this, we can simply break from the inner for loop. Now, if the inner loop terminates by exhausting all the numbers less than n, then we did not find a value that evenly divides n, so n would be prime in those cases. And to print this out, we can actually use an else statement on the inner for loop, and we'll simply print n is a prime number. Now, if I run this, we see that only the prime numbers between 2 and 10 are actually listed as prime, meaning that when the inner loop terminated due to a break statement, the print statement that was within the else did not execute. Now, to wrap up this notebook, I'm going to quickly define the pass statement that we saw earlier in the break example. A pass statement computationally does nothing. It's effectively a placeholder that can be used when a statement is required syntactically, but your program doesn't require any action. So in the text here, you can see an example of an infinite loop that does nothing until an interrupt of some type occurs that stops its execution externally. Now, more commonly, you're going to find pass statements in sort of minimal classes like my empty class here, and as placeholders and functions that need to be implemented.